Hey guys, welcome back to Crick Code. Today we're doing another Brainstellar Quant puzzle. This one is called Colored Runs of Cards. It's our first hard problem. So I'll let you guys pause and go over the problem once. So just to explain the problem real quick. So we have this standard deck of 52 cards, right? There's 26 black and 26 red cards. And it's a shuffle deck. So they've defined a term over here called a run. Now, to give you guys a few examples about how the number of runs is calculated. So consider an example where we have alternating red and black cards, right? All the way up to all the 52 cards are alternating red and black. So for this case, the number of runs comes out to be 52 because this in itself is one run, then this is one run, this is one run, and this goes on, right? Each single card will end up being one run. So 52 is the maximum number of runs that we can have for a shuffle deck of cards, and the minimum number of runs we can have is 2, which could look like something like this. So black, black, all the way. So there are first of all 26 black cards, and then there's 26 red cards all lined up together. So yeah, so this is the maximum amount of the number of runs possible, and this is the minimum amount. Now, what we've been asked is to find the expected number of runs in a shuffle deck of cards, of 52 cards, right? So we have to find the expected number of runs in a shuffle deck. So I'll let you guys pause again and try to think about ways of solving this. This is, in my opinion, a pretty tough problem, but it becomes really simple if you understand a few major points. So coming towards the hints. So first of all, let's imagine all the cards lined up, right? So this is card 1, and then we have card 2, and any general card is, we'll just call it as CI, as being the ith card. And we have this all the way up to C52, right? So there's 52 cards, and each can have a value of red or black, right? Let's not bother about what exactly is the card value. All that matters is if it's either red or black. So if I ask you guys to calculate the probability of card I and card I minus 1 being different, what would that be? So for this, there's two cases. One is where CI and CI. One is where CI is red and C of I minus 1 is black. And the other case is where CI is black and C of I minus 1 is red, right? So these are the two possible cases, right? This case and this case. So to calculate this value, we calculate the probability of C of I minus 1 equals red and C of I equals black, plus the probability of the case where C of I minus 1 is equal to black and C of I is equal to red, right? Now we can see by symmetry that these two cases are going to have the same probability. So let's just call it as 2 times the probability that CI is red and C of I minus 1 is black. And coming back to the initial question, I'll call this value X, right? X is the probability of C of I and C of I minus 1 being different. Okay, so we boiled it down to this value over here. Now, what I want you guys to focus on is that I'm going to say that the probability of this case of C of I being red and C of I minus 1 being black is the exact same as the probability of the following. So imagine a case where I minus 2 cards are arranged, and these can be arranged in whichever order, doesn't matter. Then the C of I minus 1th card is black, the C ith card is red, and then you have 52 minus I cards as in any order as you want. So this is card 1 all the way up to I minus 2. This is I plus 1 all the way up to 52, right? And this is I minus 1 and I. Now, looking at this case over here, right, what we're asking is the probability of this possible arrangement, right? So I could just say that from those 52 cards, that deck of 52 cards, I take out one card that has to be red and I give it to CI. Then I take out another card that has to be black, I give it to CI minus 1. And then all the other 50 cards are just arranged in any order. It doesn't really matter. They can be arranged in any order in these 50 remaining slots. So effectively, this value over here, the probability of Ci equal to R and C of I minus 1 is equal to black, is effectively the probability of picking out the first card as a red and then the second card as a black, and then, well, for the remaining 50 cards you can just arrange them in any order you'd like, so that won't really add anything to the equation. So the probability of the first card coming out red and the second card coming out black, and then for the remaining 50 cards you just arrange them in whichever way you'd like around those I and I minus 1th cards. So this means that the value of X is just 2 into this value over here, right? And this value is pretty easy to calculate. This is the case where we take out one card and that should be red, and then we take out the second card that should be black. So how to calculate that? Well, initially we have 52 cards and there's 26 possible red cards. So the first card coming out red is 26 over 52. And now we only have 51 remaining cards and 26 black cards. So this is exactly how this value over here is going to look like. So the value of x comes out to be 26 upon 52 into 26 upon 51 into 2. Right? This is the value of x. The most important thing to understand over here is that when I'm talking about the probability of the CIth card being red and the C of I minus 1th card being black, basically this arrangement over here, all we need to focus on is getting out one red card and then one black card. And then for the remaining 50 positions around these two cards, there's nothing to consider, right? Because any arrangement of these remaining 50 cards is going to work. We just have to calculate the probability of these two cards coming out in order. And if you look closely, then this value does not depend on the value of I at all, right? Because all we're doing is pulling out one red card and then another black card. So the probability of Ci equaling red and C of I minus 1 equaling black, or in general, the probability of C of I and C of I minus 1 being different is irrespective of the value of I, right? This is important to understand. It's irrespective of the value of I and it's always going to be equal to x. Well, in fact, for I is equal to 1, the case is going to be different because C of I minus 1 is not defined, but we'll look into that later. So once we've established this probability, the rest of the problem becomes somewhat easier. Now, it's important to realize that if Ci and C of I minus 1 are different, now how does this help me? What's the reasoning behind calculating this value in the first place? Weren't we trying to figure out the number of runs? So now let me try to connect these 2 points. So what we actually wanted, I'll just call that as y for now. What we wanted was the expected value of the number of runs in a random shuffle of 52 cards, right? So now we're going to shift the perspective a bit and say that this value is also equal to this value over here. So instead of calculating the number of runs, we're going to calculate the number of positions, right? And each position is, well, from position 1 all the way up to 52, where a new run starts. So now how do we calculate the number of positions where new runs start? Well, this is essentially equal to 1 times the probability that a new run starts at position 1, starts at C1, right? Plus 1 times the probability that a new run starts at C2. And basically the summation of all these values for all the way up to 52, right? So basically what we wanted, which was y initially, becomes this value over here, right? Because we started with it being equal to the expected number of runs, and we redefine that as saying the expected number of positions where new runs start, and that could be broken down because the e function can basically break about a summation sign. So we end up with this value over here, where we're basically summing over the probabilities of a new run starting at that position, and we do this over the summation of all the positions. So first of all, let me deal with this case independently. So if you think about it, what is the probability that a new run starts at the very first card? Well, this is always going to be 1, because from the first card we're always going to have a new run, right? Because it's the start of the deck. So no matter what is the arrangement of the cards, this position is always going to denote a start of the first run of the deck, right? So see, the probability of a new run starting at C1 is always going to be 1. But what we have to consider is these values from C2 all the way up to 52. So far we know that y is equal to 1 plus summation I goes from 2 to 52. Probability of a new run starting at C2. Ci, sorry. So this is what we're left with. This is what we have to calculate. So let's talk about this now. You pause right now and try to really think about it. This over here is essentially the same as asking the probability of Ci and C of I minus 1 being different. Because whenever C of I and C of I minus 1 are going to be different, we are guaranteed to start a new run from the value of C of I, right? Because so let's say it doesn't really matter what was before this. If C of I is red and then this is black, then from this point onwards, we're going to start a new run, right? So this value over here is the exact same as this value over here. And we've already talked about this earlier, right? This is equal to x. So it's kind of important to understand that the probability that a new run starts at the card Ci boils down to the value of x, and as we know that x is irrespective of the value of I, as in the ci value doesn't really matter, x is always the same. So the probability that a new run starts at any position, for any of the positions from the second position all the way up to the 52nd position, all of these values are the exact same, and our y value boils down to be 1 plus, well, because these are 51 values in total, 51 times x. Again, I'd like for you guys to pause and really think about this over here and try to understand that because of the way we defined x, because of the way we calculated x, by considering the case where we just need to pick out a red and then a black, or a black and then a red, and the rest of the 50 cards are arranged around them accordingly, we eliminate the dependency on I, right? So I becomes irrelevant over here. For each of these cases, from I ranging from 2 to 52, the value of the probability is always x. So this is what we boil down to, and we already know what x is. So we can just plug in that value. So y becomes 1 plus 51 times 2 into 26 upon 51 into 26 upon 52. And calculating this, we get y as 27, which is the answer to the question. So this is the Brainstellar solution over here. It's a very similar approach. It's just that the way they've gone about the approach is in a slightly different ordering. Now, if you pause and go over the solution, you might not quite understand this line over here. So the reason for this line, the reason for e of y2 being equal to e of y3 equal to all the way up to e of y52 is the exact same reason for why the probability of ci and c of I minus 1 being different is the exact same for I is equal to 2 all the way up to 52. Why is that? Because the value of e of yi is equal to the probability of yi equals to 1 into 1 plus the probability of yi equals 0 into 0, and this doesn't matter. So this is effectively just the probability of yi equals to 1. And if you've read the solution, you'll understand that this is essentially asking the probability of ci and c of I minus 1 being different, which, as we've already talked about, is independent of the value of I. It's always equal to x. So effectively, e of yi is equal to x for every value of I going from 2 to 52. So I hope you guys understood the solution, and thanks for watching.